Hello, this is a review on electricity. There may not be much pump and show here, but this is really crucial and very important that you understand what goes on in this video. There are 5 chapters essentially, and I've picked the most important equations, tried to talk about it. The first chapter is electric potential. You got to remember that electric potential is a scalar quantity. It is measured in volts and is defined as the ratio of the work done to the charge. A positive charge always has a positive potential, and a negative charge has a negative potential. Now, what are equipotential surfaces? They are surfaces that have the same potential at all points, and therefore, to move any charge from one point on such a surface to another point involves no work. Although energy is measured in joules, in electrostatics we use a unit called electron volts. 1 electron volt is 1.6 times 10 to the negative 19 joules. And whenever you work out problems, you always need to convert electron volts into joules. Potential energy is basically the product of the charge and the electric potential. Dipole moment is the product of one of the charges and the distance between the charges. Important equations: potential difference is work over charge, where work is measured in joules, charge is in coulombs, and voltage or potential is in volts. Potential energy, measured in joules, is the product of charge and voltage. Charge is in coulombs, potential is in volts. The potential difference between 2 points B and A is the negative of the integral of E dot dl between A and B. That's an important equation to remember. That gives the relation between potential difference and intensity of electric field. And then the potential due to a point charge at a distance r from it is kq by r. Remember that this k is 8.99 times 10 to the 9, but you may take it as 9 times 10 to the 9. That is the potential due to a point charge. Another way of expressing the relation between electric intensity and potential is to write it as intensity is the negative gradient of the potential. E is equal to minus dV by dr. Those are the most important equations in electrostatic potential. Take a look at this problem. An electron starts from rest. That means it has no kinetic energy. It's 42.5 centimeters from a fixed point charge with Q is equal to negative 0.125 nanocoulombs. So the electron has no kinetic energy, it only has potential energy. How fast will the electron be moving when it is very far away? So as it moves away, at a great distance away, all the potential energy it had is going to be converted into kinetic energy. That's the basic idea. So all the potential energy at 42.5 centimeter becomes kinetic energy very far away. So put the equations together. Ui is equal to Kf. Potential energy is just K times the product of the charges divided by the distance. Here K is written as 1 by 4 pi epsilon naught. Make velocity the subject, rearrange. Remember that 1 by 4 pi epsilon naught that you see down there is just K, so its value can be put as 8.99 times 10 to the 9 in the numerator. Or just substitute the entire value for 4 times pi times epsilon naught, which is 8.85 times 10 to the negative 12 times the mass of the electron times the distance. And when that is done, the answer is 9.64 times 10 to the 5 meter per second. In the second question, there is a dust particle, mass is given, charge is given. It's in a region of space where the potential is also given. And it says if the particle starts at x is 2 meter, what is the initial acceleration? See, the only formula for acceleration is force divided by mass. Force is Q times E, where E is the electric field, and the electric field can be found from the potential. So working backwards, E is negative dV by dr or dV by dx. F is Q times E. Acceleration is force by mass. Put them all together. Again, acceleration is QE by mass. And then the electric field is dV by dx. Let's find dV by dx first. Take the differential. Because it's x squared, you get 2 times. And then the second term has an x cubed, so it's 3 times x squared. Substitute x as 2 meter. Find dV by dx. Which gives negative 28 volt per meter. Now put it into the formula for acceleration, which is, that's Q divided by the mass and times negative 28. That gives 1.1 meter per second squared. Okay, those are the 2 selected questions from that chapter. Brings us to the next chapter called Capacitance. Okay, these are the equations dealing with the capacitance, and the formulas are very important. If it's a paddle plate capacitor, understand that without a dielectric, capacitance is epsilon naught A by D, but with a dielectric, it's K epsilon naught A by D, where K is the dielectric constant. Okay, if capacitors are connected in parallel, just add their capacitances to find the equivalent. If they are in series, 1 by C equivalent is 1 by C1 plus 1 by C2. Energy of a capacitor is given in 3 ways. One of them is 1/2 times Q times V, the other is 1/2 CV squared. Or there is Q squared by 2C. And for energy density, the formula is 1/2 epsilon naught E squared. Take a look at this problem. This is just an example. It's a 3.5 microfarad capacitor. charged by a 12.4 volt battery and then disconnected. This is then connected to a second initially uncharged capacitor C2. The voltage on the first drops to 5.9 volts. What's the value of C2? What is the important thing that comes to your mind when you read this question? That the total charge, even after you connect the two capacitors, must just be the charge on the capacitor which was initially charged. So the total charge does not change. Okay, total charge does not change. And the final voltage will be the same across both because both are connected in parallel. And to find the charge on the first capacitor, just multiply its capacitance with the voltage. (43.4 microcoulombs), and then find the common voltage between the two. Remember that we are adding these two capacitances because they are in parallel. The common voltage is given as 5.9, so and we already know Q. It's just a matter of rearranging this equation carefully and solving for C2. The answer is 3.9 microfarad. So the important concept here was the total charge did not change and the final voltage across both are the same because they are in parallel. Now in this question you have a 175 picofarad capacitor connected in series with an unknown, and both of them are connected to a 25 volt battery. If the 175 picofarad capacitor stores 125 picocoulomb of charge, what's the unknown capacitance? Go back to the first part, they are both connected in series. What's going to be the same? The charge on both are going to be the same. We can proceed from there. That's the important point here. In series, the charges are equal. The voltage across the first one, because its charge is given 125 picocoulomb and its capacitance is given, but the picos will get cancelled and you will get 0.714 volt. Now what about the voltage on the second one? Since we know that the total voltage is 25, the voltage on the second one should be 25 minus the voltage on the first one, which gives 24.3 volt. Now we also know that the voltage on the second is Q by C2. And since we know the voltage, we can rearrange and find the capacitance. That gives 5.14 picofarads. Brings us to the next chapter, electric currents and resistance. Point 1. Electric current is the rate of flow of charge. Usually it is the flow of electrons. But remember that the direction of flow of a conventional current is taken to be from the positive to the negative of the battery, which is exactly opposite to the flow of electrons. The most important law in electricity, Ohm's law. What does it state? The current flowing through a conductor is proportional to the voltage maintained across its ends at constant temperature. Why do we need to use the clause at constant temperature? That's because if temperature changes, the resistance will change. What is resistivity? It is the resistance of a conductor of length 1 meter and area of cross section 1 meter squared. It is a property of the material. Changing the length or the area of cross section does not change the resistivity because it depends on the material. What happens to the resistance of a conductor as the temperature increases? Well, the resistance also increases. Next, how do we calculate the electric power? There are 3 formulas. One of them is to find the product of the current and the voltage. P is IV, or I squared R, or it is V squared by R. What is the difference between direct current and alternating current? Direct currents have a constant magnitude and flow in the same direction. Alternating currents change both magnitude and direction continuously. And alternating currents are represented by a sine wave. When you take a microscopic look at the current, the formula for current becomes N times A times E times V. Okay, what are these terms? N is the number of free electrons in 1 meter cube. A is the area of cross section of the conductor. E is the charge of the electron, and this is the drift velocity of the electron. What do you mean by current density? Current density is the current per unit cross-sectional area. It's represented by J. Well, at this time, remember that the color code for resistances is important to remember. It's just given by B.B. Roy. Great Britain had a very good wife. I hope you remember that mnemonic. The first B is black, brown, red, orange, yellow, green, blue, violet, gray, white. You also know that silver is, gold is 5% tolerance, silver is 10%, and if there's no color, it's 20% tolerance. The important equations in this chapter: current is the rate of flow of charge. I is dq by dt, which gives ampere is equal to coulomb per second. Very important rule from Ohm's law. Voltage is the product of current and resistance. Resistance is given by rho L by A. Rho is resistivity. L is the length in meters. A is the area in meters squared. Power, IV, or I squared R, or V squared by R. 3 formulas. Use the correct one depending on what stays the same and what changes. Gain. For an alternating current, the representation is I naught sine omega t, where I naught is the peak value of current. Remember that the RMS value is related to the peak value by this equation. Now, if J is current density, it's given as NQVD. N is the number of electrons in 1 meter cube. Q is the charge of 1 electron, and Vd is the drift velocity. Let's do a problem. Before that, remember that J is also represented as sigma E, where sigma is called the conductivity. excuse me, many times when we use extension cords, we do not consider this. Look at this. This extension cord is made of two wires of diameter 0.129 centimeter, length 2.7 meter, connected to an electric heater which draws 15 ampere on a 120 volt line. How much power is wasted in the cord? Got to find the power. Power is given by I squared R. So first we need to find the resistance, which is given by rho L by A. And area is pi R squared. Put them all together. Current is 15 ampere. Resistivity of copper is 1.68 times 10 to the negative 8. Length, because there are two wires, is 2.7 times 2, that's 5.4. Pi R squared. Remember that it's the diameter that's given, so you've got to take half of that, change into meter. When you do all that, you get the answers 15.62 watts. Brings us to the next chapter, DC circuits. Remember that the EMF of a battery is the maximum voltage that it can give. And therefore, when you use the battery, the terminal voltage is always going to be less because of its internal resistance. Kirchhoff's rules, there are two. Junction rule, the net current through a junction is 0. And then the loop rule, the net potential difference through a loop is 0. Resistances can be combined in series and in parallel. But remember that the formulas are exactly opposite to that for capacitors. Cells can be combined. Remember that when two cells are combined in parallel, both of them should have the same EMF. RC circuits are timing circuits. And a galvanometer, which is very sensitive, can be converted into an ammeter and a voltmeter. You convert it into an ammeter by connecting a low resistance in parallel, and convert it into a voltmeter by connecting a high resistance in series. Here are the formulas. The terminal voltage is EMF minus I times internal resistance. Equivalent resistance in series is just add them up, and in parallel take the product by sum if there are only two. But this formula works for any number of resistances in parallel. Kirchhoff's current rule and the loop rule. In an RC circuit, this is the equation for charging of the capacitor through a resistance. And this is the equation for discharge. The same formulas can be used to find the voltage across the capacitor plates. Time constant of an RC circuit is just the product of the resistance and the capacitance. To convert a galvanometer into an ammeter, the resistance to be connected in parallel is given by this formula, where Ig is the maximum current through the galvanometer. G is the resistance of the galvanometer. I is the current to be measured, and to convert it into a voltmeter. V by Ig minus G. Remember that in this case the resistance is to be connected in series. Look at the circuit. It says if the switches are open or closed, both of them, the current through 20 ohms does not change. Got to find the resistance. Now first consider that S1 and S2 both are open. If both are open, then surely the current can only flow this way. that puts 20 and 50 in series, 20, 50 and 10 in series. So the total resistance is 80 ohms, and you can find the current because it's just going to be 6 divided by 80. This gives 0.075 ampere. Now if S1 and S2 are closed and you consider the outer loop as shown, the whole outer loop, and apply Kirchhoff's second rule, which is the loop rule, to that, you get 6 minus I times 50 minus the current through 20 ohms, which is given, times 20 is equal to 0. Solve for I. .09 ampere. Therefore, we can find the current through the resistance, because we know that the current has to divide the total current. 0.09 minus 0.075, which is 0.015 ampere, is the current through R. And because 20 ohms and R are in parallel, we know the voltage across both of them should be equal. So, and voltage is the product of current and resistance, they must be equal. We know 3 of these quantities, so you can find the resistance simply by rearranging and calculating. That's the current through 20 ohms. We have the current through resistance, which is 0.015, that gives 100 ohms as the answer. Let's do one more. Here you're asked to find the equivalent resistance of the circuit. If you simply take a look at this circuit and apply Kirchhoff's loop rule in this circuit, in this part, look at that part, there's the battery there and just the 18 ohms. That'll give you the current through 18 ohms. And then just when this current flows and reaches this junction, it's going to divide into two, one part through this, second through this. Therefore, we know that the current flowing through 12 and 25 are not equal. Therefore, they are in parallel with each other. So find the equivalent resistance of 12 and 25, and then the same current that flows through those two would flow through 4.5. So that is in series. But when the current reaches here again, it divides into two. So the current through 18, or rather recombines. Anyways, the current through 18 and the current through 4.5 are not the same. Therefore, this is in parallel with that. Alright, let me try to repeat what I said just now. 12 is parallel to 25, is in series with 4.5, which is in parallel with 18. Call them 1, 2, 3, 4. First R12, product by sum. That's how you find the equivalent in parallel. And then the third one is in series with it, so add it. And then the fourth one is in parallel with these three. So take the product by sum. And that gives 7.415 ohms. That's the A part. B part, what's the current? Now to find the current there, just apply Kirchhoff's loop rule in that circuit and you get the current as 0.33 ampere. What's the current in the 12 ohm? That's going to be tricky. First what we do is just take the combination 12 and 25 to be in parallel, and 18 and 4.5 are in parallel, so take that as the loop. what we did just now, right now, is to consider this loop where you take these two beats together, and that's why the value is 8.10, or it should have been 8.108 anyways. So, and then 4.5. So the loop does not include 18 ohms. Again, it has this, these two, and then this, and completed. Okay, when you solve for I from there, you get 0.4759 ampere. Now we know that since 12 and 25 are in parallel, the voltages across them should be equal. So the current through 12 is equal to the remaining current. We know the total is 0.48 minus I times 25. Solve for I. (12 by 37). That's 0.32 ampere. Find the power dissipated. I squared R. We know the current through 4.5. Square that times 4.5 will give you the power dissipated. 1.019 watts. Brings us to the last chapter, magnetism. Important rules here. The force on a current carrying conductor in a magnetic field is given by the right hand rule. And the formula is IL cross B. The force on a moving charge is F is equal to QV cross B. Velocity selector, velocity of the particles that goes through in a combination of electric and magnetic field is E by B. And remember that if the particles enter a magnetic field at an angle, it's going to be a helical path with the perpendicular component of the velocity determining the radius and the parallel component of the velocity giving the distance between the helixes, the pitch of the helix rather. The magnetic moment of a coil is NIA. Again, the magnetic moment of a coil is NIA, number of turns multiplied by the current times the area. The torque on a coil in a magnetic field is NIAB sine theta. Alright, so force on a moving charge, Q, V cross B. B is the velocity, B is the magnetic field. It's a maximum when the particle is moving at right angles to the magnetic field. Velocity selector, I said that before, E by B. If a charged particle moves through a magnetic field, the radius of the circular path it takes is R, is mv by qb. Again, the magnetic moment is NIA. Torque is on a coil suspended in a magnetic field is NIAB sine theta, which can be written as mu cross B because NIA is magnetic moment. If it's a combination of an electric and a magnetic field, the total force is given by the sum of the two forces. In fact, the vector sum of the two forces. Let's do one more problem and that'll be the end of the review. And this is an important problem at that. Excuse me, a 15 loop circular coil, 22 centimeters in diameter, lies in the XY plane. Current is 7.6, magnetic field is given. Got to find the magnetic moment, the torque, the potential energy. Moment is NIA. And because the current is flowing clockwise, if you hold the right hand with your fingers coiled around the right hand grip rule, you see that the thumb will be pointing down if the current is clockwise. So the magnetic moment is along the negative K axis. Magnetic moment is NIA. Just multiply the 3. But remember that the area is pi r squared. gives negative 4.3 K. In the B part, you're asked to find the torque. Torque is the cross product of mu and B. We already got mu. Take the cross product of mu and B. Negative 4.3 K cross product with the magnetic field. And that gives you 2.6 I minus 2.4 J. You have to remember the rules for the cross product. K cross K becomes 0. Okay, that's why that term is missing. And then you have K cross I, which is going to be J. And then you have K cross J, which is going to be minus I. So remember the rules. And the C part, potential energy, is the dot product of the magnetic moment and the magnetic field. Now it's a dot product. When you take the dot product, you remember that you only take K and K because everything else becomes 0. So you take 4.3 times 0.65, the two K values, and it's a scalar, so you get negative 2.8 joules. This review has taken 37 minutes and a couple of hours for me to prepare, so I hope you make good use of this. Thank you and good luck.